Have you ever looked up at the night sky, filled with countless stars, and wondered what else is out there? It turns out, everything we can see, from the brightest stars to the most distant galaxies, makes up less than 5% of the entire universe. The rest, about 95%, is a cosmic mystery. A huge part of that mystery is something scientists call dark matter. So, what exactly is dark matter? The honest answer is, we don't know for sure. The dark part of its name is a bit misleading. It's not dark in the way that a black hole is dark, absorbing light. It's dark because it's completely invisible. It doesn't emit, absorb, or reflect any kind of light or electromagnetic radiation. It's like a cosmic ghost, passing through us and everything we know, completely unnoticed. If we can't see it, how do we even know it's there? This is where the story gets fascinating. The first clues came from observing how galaxies move. Back in the 1930s, an astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma cluster. He calculated the total mass of the visible stars and gas in the cluster and then observed how fast the galaxies were spinning. He found something astonishing. The galaxies were moving so fast that the gravity from the visible matter shouldn't have been strong enough to hold them together. They should have flown apart, scattering across the universe. Zwicky proposed that there must be some other, invisible matter providing the extra gravitational pull needed to keep the cluster intact. He called it dunkle matter or dark matter. For decades, his idea was largely ignored. It was a radical concept, and the evidence wasn't strong enough to convince everyone. Then, in the 1970s, another astronomer, Vera Rubin, made a similar discovery, but on a smaller scale. She was studying individual spiral galaxies, like our own Milky Way. According to our understanding of gravity, stars near the center of a galaxy should orbit much faster than stars on the outer edges, just like the inner planets in our solar system orbit the sun faster than the outer ones. But that's not what Vera Rubin found. She observed that the stars on the outer edges of galaxies were moving just as fast as the ones closer to the center. This flat rotation curve was a huge puzzle. The only way to explain it was if there was a massive invisible halo of matter surrounding the entire galaxy, providing the extra gravity to speed up those outer stars. This halo was made of dark matter. Vera Rubin's meticulous work provided powerful, undeniable evidence that dark matter was real. Her observations, combined with Zwicky's earlier work, changed our understanding of the cosmos forever. Since then, the evidence for dark matter has only grown stronger. Another compelling piece of evidence comes from something called gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the fabric of spacetime. This means that light from a distant object will bend as it passes by a massive object in the foreground, like a galaxy cluster. This bending effect can distort and magnify the light from the background object, creating arcs or even multiple images of the same distant galaxy. When astronomers measure the total mass of a galaxy cluster based on the visible matter alone, the predicted gravitational lensing effect is much weaker than what we actually observed. The observed lensing is so strong that it implies there is about 5 to 6 times more mass than we can see. This extra mass, once again, points directly to the existence of dark matter. It's the unseen mass that's doing most of the gravitational heavy lifting. So, we're pretty certain dark matter is out there. It's the gravitational backbone of the universe, the invisible scaffolding upon which galaxies and large-scale cosmic structures are built. Without dark matter, computer simulations show that the universe would look very different. Galaxies as we know them probably wouldn't have formed. We owe our very existence to this mysterious substance. This brings us to the billion-dollar question. What is dark matter made of? Scientists have a few leading candidates, but no definitive answer yet. One of the earliest ideas was that dark matter could be made of ordinary, but dim objects like black holes, neutron stars, or faint brown dwarfs. These are collectively known as MACHOs, or massive astrophysical compact halo objects. However, extensive searches for these objects have shown that there simply aren't enough of them to account for all the missing mass. The leading theory today is that dark matter is composed of a new type of subatomic particle that we haven't discovered yet. These hypothetical particles are called WIMPs, which stands for weakly interacting massive particles. Weakly interacting means they barely interact with ordinary matter, which is why they are so hard to detect. Massive means that, even though they are tiny, they have enough mass to provide the gravitational effects we observe. Scientists all over the world are in a race to find these WIMPs. They're using 3 main strategies: direct detection, indirect detection, and production. Direct detection experiments are built deep underground, shielded from cosmic rays and other background radiation. These experiments are essentially giant, ultra-sensitive detectors designed to catch the incredibly rare event of a WIMP bumping into the nucleus of an atom. Imagine trying to hear a single pin drop in the middle of a rock concert. That's the level of challenge they are facing. So far, we haven't had a confirmed detection, but the experiments are getting more and more sensitive every year. Indirect detection involves looking for the products of dark matter interactions out in space. The idea is that if 2 WIMPs collide and annihilate each other, they could produce a shower of detectable particles, like gamma rays or neutrinos. Telescopes like the Fermi Gamma Ray Space Telescope are constantly scanning the skies, especially the center of our galaxy where dark matter is thought to be densest, looking for this faint signal. It's like being a detective, searching for cosmic fingerprints left behind by dark matter. The third approach is to try and create dark matter particles right here on Earth. This is one of the goals of the Large Hadron Collider, or LHC, at CERN. By smashing protons together at nearly the speed of light, physicists hope to create new particles that haven't been seen before. If dark matter is a WIMP, it's possible that the LHC could produce it. When these particles are created, they would fly out of the detector without leaving a trace. Scientists would then look for missing energy, the collision debris energy that was carried away by the invisible dark matter particle. Of course, WIMPs aren't the only possibility. There are other, more exotic candidates for dark matter. One is the axion, a much lighter, hypothetical particle that was originally proposed to solve a different problem in particle physics. Another idea is sterile neutrinos, a heavier, more elusive cousin of the neutrinos we already know. The search for dark matter is a wide-open field, with many creative ideas being explored. The quest to understand dark matter is one of the most profound and exciting challenges in modern science. It's a reminder that we are just beginning to scratch the surface of understanding our universe. What we can see with our telescopes is only a tiny fraction of what's truly out there. The universe is filled with an invisible substance that shapes the galaxies and governs the cosmos, yet remains completely hidden from our view. Every time you look at a picture of a beautiful spiral galaxy, remember that what you're seeing is just the tip of the iceberg. Surrounding that galaxy is a vast, invisible halo of dark matter, holding it all together. It's a humbling thought. We live in a universe dominated by a substance we can't see and don't yet understand. But the search continues. With every new telescope, every new underground detector, and every new particle collision, we get a little bit closer to solving this cosmic puzzle. Unmasking the nature of dark matter will not only revolutionize our understanding of physics and cosmology, but will also give us a deeper appreciation for the intricate and mysterious universe we call home. The next great discovery could be just around the corner, waiting to shed light on the darkness. Thank you for joining me on this journey into the unknown. If you enjoyed this exploration of dark matter, please consider liking this video and subscribing for more adventures into the mysteries of science. See you next time.